So how are we going to start this off to look for where we have horizontal and vertical tangent lines?
Find the derivative.
Find the derivative. So derivative of the 2x squared is 4x. And then just like that one we were talking about a minute ago with the minus 9xy, we'll do the same thing with this. How about we do it as minus 2x and y as our two functions? So we'll have minus 2x dy dx as our u times the derivative of v. And then we'll have derivative of u, which is minus 2 times our v, which should just be y. And then our y squared should be 2y dy dx. The minus 4 is 0, and the 0 is 0. Everybody good with that?
Wait, so did you use chain rule on this? Is that what you just did with all that?
Well, so I mean, I did my implicit differentiation, which is the chain rule, yeah.
Oh, you just use implicit differentiation, okay.
Right, yeah. Anytime it's got multiple instances of y, it's not y equals something all in terms of x, we want to use implicit.
And then you use chain rule within implicit differentiation?
I use the product rule. I use the product rule within, for the minus 2xy part, I use the product rule within the implicit differentiation, yeah.
Okay. Cool.
Good or no? All right. So then we'll solve for our dy dx. We can bring the 2y and the 4x to the other side. So we'll have 2y minus 4x over here. And then on this side, if we take the dy dx out, we have a positive 2y and a negative 2x. So our dy dx equals 2y minus 4x over 2y minus 2x. So far, so good?
Yep.
All right, and then I'm, just because why not make it a little bit easier, I'm going to divide everything by 2. So we got y minus 2x over y minus x. How is this one different than the ones we had been doing previously?
Variables or
There's a y in the numerator and the denominator.
That.
Yeah, right. So the other ones, it was like all y's in the numerator or all x's in the numerator, and then all y's or all x's in the denominator. But now we've got both a y and an x in each of them. So how are we going to figure out, let's do the vertical tangent lines, the locations of the vertical tangent lines first, because that should be a little bit easier. We have to make the denominator equal to 0, right?
Yeah.
Okay, so for our vertical tangent lines, we need y minus x to equal 0, which tells us that y needs to equal x. Everyone agree with that?
Yeah.
Okay. So all then we need to do is figure out when is that true in our original equation. So we're going to take y equals x, and we're going to plug that back in up here. So if we're looking for the locations of the vertical tangent lines, it'd be nice to maybe have those as x equals. So anywhere we see a y, we'll replace it with an x. So we'll have 2x squared minus, we'll replace this y with an x. And we'll replace this y with an x. And solve. And so the 2x squared and the minus 2x squared go away. What do we get? We get x equals positive or negative 2. Everybody good with that?
So those are our vertical tangent lines right there. The equations y equals 2, or x equals 2 and x equals negative 2 was our vertical tangent line solutions.
Those are the locations of where we think the vertical tangent lines will occur. If there are vertical tangent lines at both those places, then yes, those are the equations of them. But remember, we have to make sure that the values that we get for this don't also make the numerator equal to 0. That was something we talked about the other day, where like we had one that canceled out, I think.
Okay, so that's what you mean by like we think, because we have to confirm with the numerator?
Exactly.
Okay.
Yep. So we've got our horizontal tangent lines will occur when y minus 2x equals 0 or when y equals 2x. And so if y is equal to 2x, then we'll replace all the y's with 2x's, and we get 2x squared minus 4x squared plus 4x squared minus 4 equals 0. And the minus 4 and the plus 4x squareds will cancel. We get 2x squared equals 4, or x squared equals 2, or x equals plus or minus root 2. And so we'll see clearly that those are not the same, right? And so yes, there are vertical tangent lines at both x equals 2 and negative 2. And there are horizontal tangent lines at x equals root 2 and negative root 2. Now, I didn't ask you to find the actual horizontal tangent line equation, but if I did, you'd have to take this, plug it back into your original thing, and solve for y. Does that make sense to everybody?
Yeah.
Yeah.
Okay. You might have noted that the implicit differentiation stuff that I put up yesterday, I didn't make it due till Monday. It's fairly extensive. I want to make sure you guys practice this and get good at this. It's going to require some work, some practice. 1 second. Any other questions on that one before we move forward?
So when you used implicit differentiation at the top, so you went I'm trying to just figure out what you did just because you kind of did it all at once. So you went 2x squared, found the derivative of that, 4x, and then you went product rule with the negative 2xy.
Yeah,
and that's
gave me those two terms.
Okay. And then the y squared, okay, 2y dy dx equals 0. Okay. Okay, I'm good.
If you were to
Okay.
pair it, could you do -2 and x times y, or no?
Oh, like make -2 the first function and xy the second function?
Yeah.
I mean, you could, but then you still have to use the product rule for the xy part.
Oh, yeah.
So you got to use the product rule within the product rule if you do it that way.
Doesn't really make sense.
Yeah, I wouldn't recommend trying to do it that way. I mean, this way, where you write the -2 as a constant out in front, like we did with the, I think it was Evan asking about -9xy. If you put the -9 out in front as a constant and then just do the xy part by itself, that's effectively the same thing. And that's, I think, just as easy as doing it this way also. You get the same thing, though.
Got it.
How do you determine if the solutions make the derivative indeterminate?
So we'd have to have the same, like this x value of 2 would have to make both the numerator and the denominator equal to 0. But it didn't. It only made the denominator equal to 0. There's only a point on this equation at x equals 2 that makes the denominator equal to 0. The points that make the numerator equal to 0 are x equals plus or minus root 2. So if this had came out to be plus or minus 2 also, right, then we'd say that values at x equals 2 make both the numerator and the denominator equal to 0 and be indeterminate.
Okay, so there are, okay, I got it. Okay, thank you.
Yeah, but since those are different, it doesn't. Yeah.
Right, okay.
Any questions? Everybody good?
Yeah, one more. So for the horizontal tangent line, how come you start with a y equals 2x, y minus 2x equals 0 for that one?
Because that's our numerator up here. So if the full derivative equals 0, then that means that.
Okay, so yeah, numerator equals 0.
Right.
Okay, that makes sense. I forgot that part.
No problem. All right, so here's what we're going to do next. We're going to see if we can find the second derivative of something implicitly. So I want you to take about 30 seconds and find the first derivative of it on your own, and then I'll write it out and make sure we all got the same thing. And then I'm going to show you guys how to find the second derivative of it implicitly. So find the first derivative. You have like 45 seconds. Ready to go. You guys all got your derivative there?
Yeah.
All right, so hopefully you got 2x plus 2y dy dx to start equals dy dx minus 1. And then ended up with something like dy dx equals 1 plus 2x over 1 minus 2y. Is that what you guys all got? Or you might have gotten negative 2x minus 1 over 2y minus 1.
Yeah, that's what I got.
Some of you get negative 2x minus 1 over 2y minus 1. So if you got that, that's fine. That just means you move stuff to the right-hand side rather than the left-hand side. I think you're going to be happier if you convert it into this. So you'll note that both of those have negatives in front of them. So take a negative out of it and apply the negative into the denominator, and you'll get the same thing that I've got over here. Everybody good with that? Everybody see that?
Yeah.
Okay. So we're going to stick with what I've got here is the 1 plus 2x over the 1 minus 2y. And so what we want to do is we want to find the second derivative of this. So we want to take the derivative with respect to x of 1 plus 2x over 1 minus 2y. And that's the second derivative, right? Is the derivative of the derivative.
Yeah.
Yeah.
So this is a quotient of two different functions. So all we have to do is use the quotient rule. 1 minus 2y times the derivative of 1 plus 2x, which is
2.
2, minus, so that's v du minus u, and dv. What's the derivative of 1 minus 2y with respect to x?
dy dx?
It's not just dy dx, though, right? The 1 is 0. Negative 2
Oh, negative 2 dy dx.
dy dx. Everybody good with that?
Yeah.
And then all over 1 minus 2y squared. Everybody good or no?
Yeah.
Yes.
All right. So then we'll want to simplify out this as much as we can. Put a new page in here so we got some more room. So we're going to start with 2 minus 4y. Somebody out there is not muted. If you're not muted, you're not saying anything. Try to thank you. All right, and then we're going to have a minus 1 times a negative 2 dy dx, which will give us a plus 2 dy dx. And then we're going to have a negative 2x times a negative 2 dy dx, which will be a positive 4x dy dx. And then that's all going to be over still 1 minus 2y squared. And from there, what do we need to do, you think?
Factor.
Factor some stuff out.
Okay, we could factor a 2 out, I guess, if we wanted to, but what about these? We want to leave those in our derivative, or those seem like they're out of place?
Get them to the other side of the
We need to
equation.
remove them.
We need to get rid of them, right? So remember that what this is this thing that we've written here is already the second derivative. And so I don't have any other second derivatives to gather. I just have these first derivatives that I need to get rid of. How can I get rid of those first derivatives?
So you plug in the previous value?
Yep, we know what the first derivative is, right? The first derivative is 1 plus 2x over 1 minus 2y. So we're going to replace those with 1 plus 2x over 1 minus 2y. Everybody good with that?
Yeah.
Okay. Then it'd be nice to simplify the complex fraction down just a little bit. So if I were to give this a denominator of 1 minus 2y and multiply it by 1 minus 2y, what could I do with these 1 minus 2y's here?
Put them all under one fraction.
Put them all down here under one fraction. So this could be, they'd all be over 1 minus 2y, and then that 1 minus 2y would drop down here into an over 1 minus 2y cubed. And if we distribute this all out, we'll end up with 2 minus 4y minus another 4y plus 8y squared plus 2 plus 4x plus another 4x plus an 8x squared. And you'll combine your like terms and get an answer. So looks like that's 8x squared plus 8y squared. What else we got there? We got a plus 8x and a minus 8y. And then a plus 4.
Yeah.
All over 1 minus 2y cubed. Everybody good with that or no?
Yeah.
Yep.
You want to factor a 4 out of the numerator, go for it, but there's no particular reason to do that. All right, so we need to be able to find second derivatives implicitly also. Generally on the AP test, there is one question somewhere in the AP test where they have you do this. So, there's only, how many questions are there? 51 questions on the AP test. So 1 out of 51 questions, they're going to ask you to do this. So be ready for that. All right. You guys want to try and do one on your own and see if you can get it, and then we'll come back and go through it together? All right. So take about 2 or 3 minutes and get the first derivative, and then you can start the second derivative. But after a minute or two, I'm gonna make sure everyone has the right first derivative before anybody goes too far to find the second derivative. So take a couple minutes and do, if you can get as much done as you can. All right, so just to make sure we all got the first derivative, the xy should have been x dy dx plus y times 1 for the product rule on that, and then minus 2y dy dx minus 1 equals 0. And so you would have ended up with dy dx equals the 1 comes to the other side and the y is subtracted to the other side. And then we factor out the x minus the 2y. Is that what you all got for your first derivative?
Yes.
All right.
Yep.
Some of you still working on your second derivative?
Yeah, I just need a few more.
Yeah.
All right. Yeah, no worries. I'll give you guys 2 or 3 more minutes to work on your second derivative. And in fact, you might need a little more than that to simplify it, but I'll give you at least 2 or 3. So keep working. Are we ready to finish this one up?
Yeah.
All right. Our second derivative, since this is a quotient of two functions, we'll have to use the quotient rule. So we'll take the denominator, x minus 2y, times the derivative of the numerator, which is the derivative of 1 is 0, and the derivative of negative y is negative dy dx, and then minus 1 minus y times the derivative of x minus 2y, which is 1 minus 2 dy dx, all over x minus 2y squared. Everybody good with that or no?
Yep.
All right. Cool. So then we're going to replace these dy dx's with our original dy dx's. So I'm going to do this on a new page. So we've got a negative and we've got an x minus 2y. Then we have our dy dx, which was what, 1 minus y over x minus 2y. And then the second part of that is we'll need to distribute this stuff all out, right? Because this has a 1 minus 2 times dy dx, so the whole thing's not being multiplied by dy dx. So the 1 minus the 1 should be minus 1. So we'll have a minus 1, and we'll have a plus y to start with. And then we're going to have a minus 1 times a minus 2, which is a plus 2 dy dx. And then we'll have a minus 2y. So a plus 2 and a minus 2y. Times dy dx, which was 1 minus y over x minus 2y. All over x minus 2y squared. Everybody good with that?
Yeah.
Okay. And so what do we need to do? We need to multiply the negative 1 by 1 minus y over x minus 2y. And we need to do the same with this this y, not by 1 minus y, but by x minus 2y over x minus 2y to both the negative 1 and the plus y. Everybody good with that?
Yeah.
So we're going to give that an x minus 2y. We're going to multiply this by x minus 2y also. And we could distribute it all out if we want to, but I'm not going to bother. So should be a minus 1 should be inside there. So plus x minus 2y times negative 1 plus y, then plus 2 minus 2y times 1 minus y, all over our x minus 2y cubed. Good or no?
Yep.
And if you want to, you could distribute and combine like terms, and some of it will simplify down, but not necessary. You don't even have to get that common denominator if you don't want to. And sometimes it's nice to. Might need to in the context of the problem. So. But for right now, there's no context to this. So. Everyone good? Any questions? Any issues with that?
How did you get the 2 minus 2y times 1 minus y over x minus 2y?
Down here, we were distributing the minus a minus y times the negative 2 and the minus the 1 times the negative 2 dy dx. So minus 1 times negative 2 would be plus 2 dy dx. So that's why I got a plus 2. And then the minus y is a plus y times the minus 2 gives us a minus 2y dy dx. So that's our minus, or is it, or minus 2y. And then the dy dx is the 1 minus y over x minus 2y that we threw in there.
Got it. Thanks.
Yep, no problem.
So would you recommend replacing the dy dx's before you expand the equations?
It doesn't really matter. You could expand it out first and then do it. Or, I mean, I would probably expand it all out first if you're planning on expanding it all out first. Like if there's a reason to expand it all, do that first and then replace them. But if there's not a reason to expand them, then don't even bother. Just replace them right away and box your answer and say you're done.
Okay. Thank you.
Yep. Any other questions on that? Finding second derivatives using implicit differentiation.
Why does, for the final answer, why does it become, the denominator become x minus 2y to the power 3?
Because each of these pieces in the numerator has x minus 2y as the denominator, right? And so if I put those all together as one fraction, right, this whole numerator over x minus 2y is the numerator of my complex fraction, then my denominator would be x minus 2y to the second over 1, right? And if I flipped and multiplied, that x minus 2y that's underneath all of these would be multiplied by the x minus 2y squared.
Right, okay.
Does that make sense?
Yeah.
Yeah. Any other questions there before we move on? All right, so we're going to change gears slightly, actually more than slightly. I have one thing that I want to show you guys how to be able to do, and that's to evaluate derivatives at certain points using your calculator, because you will need to be able to do this on the AP test, assuming we have an in-person. You guys can't hear me? It says it's connected. Can you guys hear me now?
Yes.
Yeah.
Yeah.
All right, I don't know what happened there for a minute, but looks like we're good now. So we're changing gears almost completely here. For one thing that we need to know how to do with derivatives, and that's how to evaluate them at points using our calculator. So if I asked you, if I said to you, oh, what's the derivative of x squared at x equals 3, you'd find the derivative of x squared as 2x, right? And you'd just plug in 3, right? We've done that to find the slopes of the tangent lines a bunch of times. True? Hopefully. So we are also going to be able to use our calculators as a tool to help us evaluate derivatives of functions at certain points, especially when the derivatives or the functions that we're given are pretty unpleasant looking functions that we don't really want to have to differentiate. Right, this one, first of all, we don't know how to do an inverse trig function yet, and we also don't know how to do logarithmic functions yet. But even if we did, we'd still have to do the product rule for these, and within the product rule, we'd still have to do the chain rule for each of them. So this derivative would be quite a pain. So you should all have a graphing calculator. Is that true?
Yeah.
All right, so if you have a graphing calculator, or if you've downloaded the one I put a link up to download at the beginning of the school year, take that out, and I'm going to pull up the graphing calculator. Hopefully. Thought I was going to. All right. So I've got my graphing calculator here. First thing, you guys all have your calculators? You all ready?
Yep.
All right. First thing is, unless you specifically need to be in degrees, make sure you are in radians. So hit mode and make sure you're in radians. Don't change that to radians unless I tell you that we're needing to do something in degrees. And so everybody in radians, everybody sees radians down there, select radians from mode, okay. Okay, so in order to find a derivative at a point using your calculator, you're going to go into this math window. And you're going to go down to option 8, which is in deriv. And hopefully it should pop up and look like my screen does. Anybody's not look like that? Anybody's say in deriv and then have a parenthesis?
Mine does.
Okay, who said that?
That was Lorelai.
Lorelai, okay, did you get your calculator from the library or is it one you already had?
It's one I already have, the 83 plus.
83 plus, okay, yeah, so that's fine. It's still gonna do everything you need it to do. You can just ignore me for a second here and then I'll tell you what to do with your calculator that's almost the same.
Okay, thank you.
Yeah. What was that? Somebody else say something?
Mine doesn't have that either. I have an TI 86.
86. Oh man. What is it? Does it just say in deriv?
If I go to math,
I cannot hear you. I don't even know
No.
what. No, there's no in deriv in math. Okay, so you're gonna need to either get out your manual for your calculator or check out a calculator from the school library. I know that you can still get in and do that. They should have, I don't know why they didn't tell you to check one out when you were at kickoff. They should have told you to check one out when you were at kickoff, but yeah. Get in there and get yourself a calculator. I can figure out what days they're available. I know they sent a thing to us a few days ago with those days, but I don't remember offhand what days they're available for checking stuff out. But you're going to want a TI 84 plus if possible. Okay. All right. So for those of you that are here at this screen, all you're going to do is, since we're looking for the derivative with respect to x, you're going to type an x there. And then you're just going to type in your function, which was, I don't even know, what was our function? It was the inverse cosine of x to the third or to the second?
Third.
Third, okay. And then what was it? The log base 10. If you just hit log on your calculator, that's log base 10 of what? Of x squared. And then you're just going to put in the value that I have in the x equals whatever I asked you to evaluate at, which I think was 0.45. Or was it 0.35? 4.5. Yep. And so then it will evaluate the derivative of that at x equals 0.45. Is that what you all got? 3.278925135?
Yes.
Cool. So Lorelai or anybody else that doesn't have the ddx that shows up, if it just shows up as in deriv, what you're going to do is you're going to type the full function out inside those parentheses. Then you're going to type a comma, which is right above your 7, probably. And then you're going to type an x. And then you're going to type another comma. And then you're going to put in your 0.45 value, close your parentheses, and hit enter. And it should give you the same thing. Everybody good?
Yeah, I got it. I got it.
All right, Lorelai, you got it, and everybody else got it on their other calculator, their non-TI-83 plus calculator?
Yeah.
Yeah, and Lorelai, yours, I mean, you're going to have to do this, just type yours in differently, and there'll be one other thing that you'll have to do differently with your calculator. But other than that, yours does everything that the TI-84 will do, except for have nice looking notation. So,
Okay, thank you.
no
So
problem.
everything that we've done so far can be solved with this calculator. Is that true?
No, your calculator will not take the derivative for you. It won't like just tell you algebraically what the derivative of the inverse cosine of x cubed times the log base 10 of x squared is. It will just approximate for you what the value of the derivative at an x value for that function is. So some of the things you could have plugged it in and had it do it for you, but you still need to be able to take all these derivatives algebraically. And then there's another way that you can also do this. If you were to go into your y equals here and you were to graph your function, again, we'll do the same function, cosine of x cubed. What is it? Log. All that. Oh, geez. That didn't work. Let's try that again. Cosine of x cubed times log of x squared. And you were to graph that, and see it looks like this. You can also, when you're in the graph of the function, hit second and then trace, which takes you to the calculate window. And you can choose option 6, which is dy dx. And you'll just, it goes straight back to the graph and you just type in 0.45 and it's going to evaluate the derivative for you at 0.45. And you can see it says that it's 3.2789251, which is what we got the other way.
That works for me. I was able to do that on my calculator.
On the 86?
Yeah.
Okay, well then, yeah, you should be okay then, probably. When you just,
Sorry,
just to make sure.
How'd you do it with the graph?
So once you've graphed it, you do second and then trace. It takes you into this calculate window. And it's option 6, dy dx. And then once you hit option 6, it just brings you to the graph. Just type in 0.45 and hit enter.
Okay, got it.
Yeah.
Thank you.
Yeah, and who was it that has the 86?
Me.
Who is me?
Sean, Hashem.
Okay. Oh yeah, right. Elon's brother. All right. So when you go in, just to make sure, if you go back into the second trace window, does it also have this number set option 7 there?
Yeah, it does.
Okay, then you should be able, I think, to do everything that we need to do with that 86. I think. If we get through partway through the year and you can't, then we'll have to figure it out from there. But hopefully halfway through the year, we'll be back in the classroom and I have extra graphing calculators if you need one that's not an 86. So. All right, so the next thing we were gonna do, we'll just do one more problem real quick here, maybe. We'll do a couple more of these. All right, so let's look at this next one that we had going on here. We have a particle moving along the x-axis so that at time t greater than or equal to 0, its position is given by this x of t equals cosine root t. And we want to know what is the velocity of the particle the first time the particle is at the origin. You guys can see the problem now, right? Not the calculator.
Yeah.
Okay, so we want to know the velocity of a particle the first time it's at the origin. And this is its position function. So we're going to use a calculator to do the majority of the work here. If we want to know when the particle is at the origin, what is its position at the origin?
0, 0.
Right. And so the t value, sorry, we want to figure out what the t value is when it's at that origin. So So when we say 0, 0, it's moving along the x-axis, so we don't need to worry about the y-coordinate of it. The y-coordinate doesn't actually matter, right? Because it's just moving back and forth along the x-axis. So all that really matters is that the x-coordinate, this x of t position here, is equal to 0. So if we can set cosine of root t equal to 0, then that should give us the position, I'm sorry, the time at which the position is 0. Does that make sense, everybody?
Yeah.
Okay. So we could algebraically solve this. It's actually not that difficult to do, but I just want to make sure we're at least marginally comfortable with our calculator. So we could go in here and graph the function cosine of the square root of x, right? Since we can't do a t, cosine of the square root of x. And if we want to know when that is equal to 0 for the first time, all we have to do is look at when it crosses through the x-axis, right? And so hopefully you know how to calculate an x-intercept using your graphing calculator. But if you don't, we're going to do it right now. It's second. And hopefully you're all following along with your calculators right now, right?
Yes.
Okay, so second, and then trace again, which is the calculate window. And you're going to choose option 2, 0, right? You're going to figure out when it has a 0, when it crosses the x-axis. And what it does is it will tell you, first off, it'll say left bound. So what you're going to do is you're going to just make sure that your cursor is on your graph somewhere to the left of where that x-intercept is. Okay? And you're going to hit enter. Then it will say right bound, and then you're going to scroll over to your cursor somewhere to the right of that x-intercept. And you're going to hit enter again. Then it's going to say guess, and you're just going to hit enter again. And it's going to tell you that that root occurs at about 2.4674011. Everybody good with that?
Yeah.
So what did I get? 2.4674011. That's what I had. Yeah. And so if this was the AP test and they gave you a calculator to do this, your first step would be good enough here. You'd show what equation you're solving, and then you'd use your calculator to solve it. So that's when the particle is first at the origin, but we want to know what is the velocity of that particle at the first time it's at the origin. So how would we figure out the velocity if we're given a position equation?
Find the derivative of the position.
Find the derivative of.
Yep, exactly.
Cosine root
So we want to find the derivative with respect to t of cosine of root t. And what do we want to do with that once we found it?
Plug
We want to evaluate it.
0?
Not 0, but we want to evaluate it at this t.
Oh, at that t.
At 2.4674011. And so there's no reason for us to actually calculate that derivative by hand since we're given a graphing calculator for this problem. So we will go back in, second, calculate, choice 6 now, dy dx, and we'll do it at 2.4674011. Don't ever round until your last answer. So our derivative there at 2.4674011, that's not, oh, there it is. That's the y value. Our derivative is negative 0.31831. Everybody see that? Is that what you got on your calculator?
Yeah.
Yeah.
All right. Negative 31831.
Yeah.
Yeah. And so on the AP test, when you round, you can go to more than 3 decimals, but never round to less than 3 decimals unless it specifically asks you to. So you're always going to round to at least 3 decimals, and you're never going to round until you get to your final answer. Is everybody good there?
So didn't we just find the derivative of cosine of square root t? When did we evaluate it at that specific x, or did the calculator just do that on its own?
The calculator did that for us. The calculator said we're going to, what we did on the calculator was we found the point, or we found that x value, and then we said what's the derivative at this x value, and it was negative 0.31831.
Okay, so if you already find that, or you already have like that point in and you hit derivative, it evaluates the derivative at that point. Is that
Well,
what
no,
you're saying?
I mean, I had to type in the 2.46740.
Oh, yeah.
But
Okay.
Yeah.
Oh, yeah, I remember doing that now. Cool. Thanks.
Yep. All right, we are going to stop with that for right now. I'm going to put a couple of problems for you guys to practice using your calculator up. Perhaps, yeah, probably, I might put them up this afternoon, but I'm not going to have them due until sometime next week, probably like Tuesday or so, because I already have that implicit differentiation set of problems due on Monday. And we got to get some more implicit differentiation ones up with second derivative too. So we got quite a bit we got to be practicing and working on